we have so far discussed this property of compactness, I mean definition, examples and various equivalent conditions of compactness, etc. We shall now discuss certain properties of continuous functions defined on compact sets. Of course, one property we have seen already, that is the namely that the continuous image of a compact set is also compact. Let us start from that. Let us also recall the following thing, that is, suppose we have, let us say, two matrix spaces xd and let us say y rho are matrix spaces, and suppose f from x to y is a function. Okay. We already know what is meant by a bounded set in any matrix space. Okay. Let us again recall it. Bounded means its diameter is finite. Okay. And using that we can also say, when will we say that the function f is bounded. Okay. We will say that f is bounded if its range will be a subset of y. If that is a bounded subset of y, we shall say that f is bounded. Okay. So f is said to be bounded. I mean, this is the usual definition, we have already used it. Okay. Said to be bounded if f of x is a bounded subset of y. Okay. We may also consider some subset of x. Okay. And for example, a is a subset of x and say that f is bounded on a. Okay. It will mean that f of a is a bounded subset of y. Okay. That is the usual terminology. Okay. Then let us now say that what we have seen is already is this, that is, suppose E is a compact subset of x. Okay. And f is continuous. And f is continuous. Okay. Then we have already shown that if E is compact and f is continuous, then f of E is also compact, right? Then f of E is also compact. Then f of E is compact. Compact means compact subset of y. Okay. And we have already seen that every compact set is closed and also bounded. Okay. In fact, we say something more. In fact, it is what is called totally bounded. Okay. But let us not bother about that right now. It is at least bounded. So in particular, what this means is that then f is, so this in particular implies that f of E is bounded. F of E is bounded, and that is same as saying that f is bounded. Okay. Right. So what we have observed is that every continuous function defined on a compact set is bounded. Okay. Continuous function defined on a compact set is bounded. Okay. All right. We can say something more if this space y is R. Okay. If this space y, that is, if it is a continuous real valued function defined on a compact set, then what we can say is that not only that the function is bounded, but its bounds are attained. That is, we can find a point at which the function takes its maximum value, and similarly we can find a point at which the function takes its minimum value. Okay. So let us take that. Suppose suppose f from x to R is continuous. Okay. And let us again take that E is a compact subset of x. Okay. Suppose E is a compact subset of x, then f of E is closed as well as bounded, right? F of E is compact and hence closed as well as bounded. Okay. So f of E is closed and bounded. Okay. And we have observed in R there is no difference between bounded and totally bounded. Okay. These two concepts coincide in R. Okay. Since it is bounded, we can say that there exists some supremum. Okay. There exists some supremum. So let us say that let alpha belong to, let alpha be the supremum of this f of e, okay, see, fine, supremum of f of e, that is same as supremum of fx, x belongs to e, okay, or which is better to still we can say this is same as what we can say supremum of f of e, right, that is the same thing, right, okay. And we have already seen that when you talk of subsets of R, then supremum is a point of closure, right, supremum of a set or least upper bound of a set is a point of a closure. So if it is a closed subset, then the supremum belongs to that set, okay. Similarly is the case of infimum, right. So this alpha, since f of e is closed, that implies that alpha belongs to f of e, okay, that means that alpha belongs to f of e, okay, that is we can say that is there exists, let us say, some x1 in E such that f of x1 is equal to alpha, okay, f of x1 is equal to alpha. Similarly, instead of the supremum, suppose I take infimum, okay, suppose I take, let us say, suppose I take beta as infimum of this same set, then this is also a point of the closure of f of e, okay. So we can similarly say that beta also belongs to f of e, okay, and so we can similarly say that there exists some point x2 in E such that f of x2 is beta, okay. So now if you take any point x in E, the value of fx must lie between beta and alpha, or in which is same as saying between f of x2 and f of x1, okay. So now what we can say that for all x in E, since this beta is f x2, this should be less than or equal to fx, and this should be less than or equal to f of x1, and f of x1 is alpha, okay, right. That means these 2 points x1 and x2, at x1 f attains its minimum, at x2 f attains its maximum, okay. So if f is a continuous real valued function defined on a compact set, okay, then it is bounded, that is, in fact, boundedness is true whatever be y, okay. In case of real valued functions we can say something more, it is bounded, and not only that, the bounds are attained, okay, that is there are points at which f attains its maximum value as well as minimum value, okay, right. The way in which we come across this property is that, see, in many applications this function is defined on some closed interval, closed and bounded interval, okay, and we know that is a compact set in the real line. So every function defined on a closed bounded interval will attain its continuous function will attain its maximum as well as minimum, okay. Then let us also take one more thing. Suppose this map f is bijection, suppose f is both 1 1 and on 2, okay, then we know that inverse function exists, okay. Now if f is continuous, f inverse may or may not be continuous in general, okay, but if x is compact, then whenever f is continuous bijection, its inverse is also a continuous function, okay. So that is a very important property, so let us, or important theorem rather, let us prove that as a theorem, okay. So suppose f from x to y is continuous bijection, suppose f from x to y is a continuous bijection, okay, then of course once it is a bijection the map f inverse is defined, okay, the map f inverse is defined, okay, but it may or may not be continuous in general, okay, but if x is compact then f inverse is also continuous. So if x is compact, then f inverse from y to x is continuous. In other words, we can say that, see, we have already seen that if a map is a bijection and if both f and f inverse are continuous, we have called such a map homeomorphism, right. When f as well as its inverse are continuous, we have called it homeomorphism. So what this says is that every continuous bijection on a compact metric space is a homeomorphism, right. Okay. All right. Now what do we need to prove here? We need to prove that this is continuous, okay. Okay. Now how does one prove that a map is continuous? Well, there are several ways. You can either use that epsilon delta definition, or we have shown that equivalently one can show that inverse image of an open set is open, right. Inverse image of an open set is under a map is open. Is it also clear to you that it is also equivalent to saying that inverse image of a closed set is closed, okay? Because closed sets are nothing but the complements of open sets, and under a bijection complements are also preserved, okay. So it is enough to show that inverse image of a closed set is closed, okay. But inverse image under which map? We want to set f inverse is continuous, okay. So inverse image under f inverse, okay. But is it same as saying that is it same as saying that inverse image under f inverse means nothing but a direct image under f, right. You are taking inverse image under f inverse of some set, which is same as direct image of under f of the same set. In other words, what we need to prove is that if you take a closed subset of x, then its image is also closed. If we show that, it will mean that f inverse is continuous map. Is that clear? Once that is clear, then you will see that once this is clear, then the proof is very easy, okay. It follows from whatever we have proved earlier, okay. So let us first observe this. It is sufficient to prove this. It is sufficient to prove that it is sufficient to prove what? If E is a closed subset of X, then f of E is a closed subset of phi. Okay. So let us start from this, okay. Suppose let E be a closed subset of X. Okay. Okay. But we have assumed that X is compact, remember, okay. Okay. And what can you say about a closed subset of a compact set? It is also compact. We have seen that a closed subset of a compact set is compact, okay. So then E is compact, okay. Okay, this is because we have assumed that X is compact, okay, right. Once we say E is compact, what can we say about f of E? F of E is also compact, because we have said that f is a continuous function, remember we have shown that f is a continuous function, okay. Okay, so then f of E is compact. What is the reason for this? This is because f is continuous, okay. But once f of E is compact, it follows that it is closed, okay. We have already shown that every compact set is closed, okay. So this implies that f of E is closed, okay. All right. Okay. Let us also recall that we have seen what is meant by saying that a function is uniformly continuous. and we know that function can be continuous but need not be uniformly continuous. Uniform continuity is a stronger property. We have seen examples of functions which are continuous but not uniformly continuous. Now what we want to say is that this sort of thing will not happen on compact sets. On a compact set, if a function is continuous, then it must be uniformly continuous. Okay. So remember, all along we are actually explaining how compactness is a very important property, how it leads to many important and useful things. Okay. So let us now go to prove this theorem. Okay, let me just say this. Okay, suppose now I take xd two metric spaces and f from x to y, let us say continuous function. Okay, so what I want to say now is that if f is continuous, if x is compact, then f is uniformly continuous. Okay, or in simple language, every continuous function defined on a compact metric space is uniformly continuous. Okay. All right. Okay, there are several ways of proceeding with the proof. Okay. In fact, there are many known proofs of this theorem. Okay. I shall now discuss the proof which is given in Rudin, and when I give you the next problem sheet, there I shall give you the certain steps in other proofs as exercises. Okay. So anyway, what is needed to be proved that to show that f is uniformly continuous? That given any epsilon, there should exist some delta which is independent of x. Okay, that is what we need to prove. Okay. So let us start with that. Okay, so let epsilon be bigger than 0, and our aim is to find a delta which corresponds to this epsilon, such that if you take any 2 points x and y in x with the distance less than delta, then the distance between fx and fy should be less than epsilon. Okay, all right. But what we know right now is that f is continuous. Okay, so given any x, there will certainly exist delta which works for that particular x. Let us start from that. Okay, so let us say that let us take any x in x. Okay, then since f is continuous at x, there exists some delta which does not require, so that delta may depend on this particular x. Okay, so then there exists, so let me call it delta suffix x, then there exists delta x bigger than 0 such that for all xy in x with dxy less than delta x. In other words, this is same as saying that if y belongs to the open ball with center at x and radius delta x, then the distance between fx and fy should be less than epsilon. Okay, this distance is rho, so rho fx fy is less than epsilon. Okay, less than epsilon, but I cannot take epsilon or any other small number. I can also say less than epsilon by 2, epsilon by 2 or 2 epsilon or epsilon by 3, it is okay, any number I can take which is suitable for me to use in the subsequent steps in the proof. Okay, if this is not suitable, we can change it later. Okay, so for the time being I will take epsilon by 2. Okay. Now see, it is a usual way of using the compactness is the following. Okay, because we know that how does one use compactness? We know that by compactness we mean that every open cover has a finite subcover. Okay. So all proofs, you would have observed by now that all proofs using compactness, what they will do, that for each x you construct some open set which contains that x, then family of all such open sets will cover x. and then extract a finite subcover from that. That is the idea. So now what I do is that, okay, for each x I have this delta x, okay, we take an open ball with center at x and radius either delta x or again delta x by 2 or delta x by 3, we shall adjust that, okay. So for the time being I will start with delta x by 2, okay. So suppose I take this open ball with center at x and let us say radius delta x by 2, okay, and take the family of all such open balls x in x, okay, then this is an open cover of x, okay, this is an open cover of x. And since we have assumed that x is compact, okay, this has a finite subcover, okay, open cover of x, and hence, and since x is compact, has a finite subcover. Finite subcover. Say that finite subcover involves n points x1, x2, xn, etc. Okay, so say u x1 delta x1 by 2, u x2 delta x2 by 2, etc. Let us say there are n such points u xn delta xn by 2. What does this mean? That if you are given any point x in x, any point small x in big X, that must lie in one of these balls, okay, each x, that means given any x you should be able to find some j such that x belongs to u xj delta xj by 2, that is in other words distance between x and xj should be less than delta xj by 2, okay, for each x such j should exist, okay. Now let us take delta to be minimum of all these numbers, there are n such number, okay, delta x1 by 2, delta x2 by 2, etc. So let delta be minimum of delta x1 by 2, etc. Okay, then see it is here that we are basically using that this is a finite subcover, okay. So this is a finite set and each of this number is strictly bigger than 0, so the minimum among them is also strict, is in fact one of these numbers, minimum is one of these numbers, so that should also be strictly bigger than 0, okay. If you take infinite set where each number is positive, then the infimum over that may not be positive, okay, that can be 0, okay. So that is where we use the finiteness here, okay. So we have found a delta such that delta is bigger than 0, it is a minimum of this, okay, and obviously our idea is to show that this is the required delta which works for all x irrespective of x and y, okay, alright. So now let us see how that can be shown. So now let us take any 2 points x and y such that the distance between x and y is less than delta, okay. So let xy be in x with distance between x and y less than delta. And our aim is to show that the distance between fx and fy should be less than epsilon. Okay, let us use whatever we have done so far. So since x is in x, we can say that for this x there exists some xj, such that distance between x and xj is less than delta xj by 2, okay, right. So we can say that there exists j in this set 1 to n such that distance between x and xj is less than delta xj by 2, okay. And of course delta xj by 2 is obviously less than delta xj, okay, and hence distance between fx and fxj, that will be less than epsilon by 2, okay, that will be less than, because we have seen that if the distance between x and xy is, if distance between any 2 points is less than the delta suffix x, the distance between corresponding fx and fy should be less than epsilon by 2. So this implies distance between fx and fxj, this is less than epsilon by 2, okay. Remember our object was to show that distance between fx and fy is less than epsilon by 2, okay. So one way of achieving that is to show that distance between fy and fxj is also less than epsilon by 2, okay. That we can do if we show that the distance between y and xj is also less than delta xj, okay. So consider distance between y and xj, okay, distance between y and xj. Obvious thing to do here is that since we know something about distance between x and xj, and we know something about distance between x and y, and we want to know distance between y and xj, just use triangle inequality, okay. So this is less than or equal to distance between y and x plus distance between x and xj, okay. Alright, what do we know about this distance between y and x? That is less than delta, right, okay, and distance between x and xj, that is less than delta xj by 2, right, okay. Distance between x and xj, that is less than delta xj by 2, okay. Alright, now how is this delta and delta xj related? It is minimum of this, all this, okay. So I can say that this is also less than or equal to delta xj by 2, right. So the sum is less than or equal, less than delta xj, okay, right. And if, and hence now we know the distance between y and xj is less than delta xj, and hence the distance between fy and fxj should also be less than epsilon by 2, okay. So this implies distance between fy and fxj is less than epsilon by 2, okay. Now I think we have everything that we require. So consider now distance between fx and fy, okay. So this is not equal to, again by triangle inequality, distance between fx and fxj and plus distance between fxj and fy, okay. And we have shown that each of the term occurring on the right hand side is less than epsilon by 2, okay. That is, this is less than epsilon by 2, that we have shown here, okay, and that the last term is less than epsilon by 2, that we have shown here, okay. So this whole thing is less than epsilon by 2 plus epsilon by 2, that is equal to epsilon, okay. So we started with an epsilon bigger than 0, okay, and we obtained a delta with the property that if the distance between x and y is less than delta, then the distance between fx and fy is less than epsilon, okay, and this delta is independent of x, okay. We have taken any two x and y in x, okay, and we have shown that if the distance between any two x and y is less than delta, then the distance between fx and fy is less than epsilon, okay, right. So that shows that f is uniformly continuous, right, okay. Remember, we have used the compactness of x here to obtain this finite subcover to get this delta, okay, and we have used the continuity of f here, that is there will exist delta which depends on x, okay. Right. Obviously we have used several things using compactness, okay. Obviously if the compactness is not there, okay, then we should expect that these conclusions do not follow, okay, right. But of course saying that this proof uses compactness and hence the conclusion does not follow is not a correct argument, because we can always think that there may be some other proof, okay. So to show that the conclusion does not hold, there is only one way, okay, and what is that way? You must give a counter example. So in this case what does it mean? That give a counter example, if x and y are metric spaces and f is a continuous, so f is continuous, if x is not compact then continuous but not uniformly continuous. Similarly in the earlier theorem, f from x to y is a continuous bijection, okay, but f inverse is not continuous, okay. And similarly the earlier properties, okay, for each of those properties, see whatever we have discussed today, various properties of continuous functions defined on compact sets, try to drop the compactness and get a counter example. So that will be a set of exercises for you. Now we shall pay some attention to the functions defined on subsets of the real line, okay, and let us see how some of these ideas apply there, okay. Of course already we have seen the functions which go to the real line, okay, but now we shall also think of functions which are defined on subsets of real line. So in other words, for the conditions that we are going to discuss, it is convenient to take open intervals a b, okay. Let us say some a less than b and take the open interval a b and consider f defined from a b to r, okay. And suppose we look at say x in a b, okay. We have already defined what is meant by saying that f is continuous at x, okay. F is continuous at x, okay, and if f is not continuous at x, we say that x is a point of discontinuity of f, okay, right. So we will say that if f is not continuous at x, then x is said to be a point of discontinuity of x, f. Okay. What we want to discuss now is that what are the points of discontinuity of a given function f and what are the types of discontinuity, okay, or in what way this can happen, that is in exactly how many ways f can be discontinuous at x, or f can fail to be discontinuous, f can fail to be continuous at x. Remember that we have seen that when we are talking about continuity, if x is an isolated point then f is always continuous at x, okay, but that will not happen in this case because it is an open interval and x belongs to the point in the open interval. So x is not an isolated point, x is always a limit point, okay. And what we have seen further is that if a point is a limit point, then f is continuous at x is equivalent to saying that limit of, okay, since we are taking the property, let us say limit of ft as t tends to x, this limit should exist and its value should be same as f of x, that is if f is continuous at x. Okay. But if it is not, then one of the two things should happen, okay. Either that this limit does not exist, okay, or the limit exists but its value is not same as this, okay. If its value is not same as this, okay. The second type, that is the limit exists but its value is not same as this, okay, that part is called, that is if limit t tends to x ft exists, okay. Suppose this limit exists, okay, then what are the ways in which f can fail to be continuous? Only way is that its value is not same as fx, okay. Then that kind of discontinuity is called removable discontinuity, okay. So if limit t tends to x ft exists and x is a point of discontinuity, okay, then x is set, then let us say f is said to have removable discontinuity. Removable discontinuity at x. So this is, in other words, what we are doing is that we are classifying discontinuities, okay. In other words, we are considering what is called types of discontinuity, okay. Types of discontinuity, okay. So this is one type, namely removable discontinuity. Why it is called removable? Because if this is the case, what we can do is that we can redefine the function at x and make its value equal to this limit, and the new function will be continuous. That means we can remove the discontinuity by changing the definition of function at that point x, and that is why it is called removable discontinuity, okay. And for all practical purposes, removable discontinuity is as good as consider the point of continuity, okay. So we simply ignore the removable discontinuities of the function, okay. So we only talk of those discontinuities which cannot be removed in this fashion. That means what? That means this limit does not exist, okay. That means this limit does not exist, okay. What we shall do further is that we want to further classify those discontinuities, okay. And to do that we will also define what is called, okay, you must have heard of these things in your undergraduate course also, but let us recall again, okay, what is called left hand limit and right hand limit of a function, okay. Let us again use Rudin's notation. F of he denotes as f of x plus and f of x minus, okay, f of x plus and f of x minus, okay. Okay, let us first recall this. Suppose limit of ft as t tends to x, okay. Suppose that limit is equal to L, okay. Now what is the meaning of this, okay? We have seen that this means that for every epsilon bigger than 0 there exists delta bigger than 0 such that mod x minus t less than delta, okay, let us say 0 less than mod x minus t less than delta. This implies mod ft minus fx is less than epsilon, okay. And we have seen the geometrical interpretation of this. this means that mod x minus t less than delta means that t lies between x minus delta and x plus delta, that is you take this interval, say suppose this is x plus delta and this is x minus delta, okay. T lies between x minus delta to x plus delta. If t lies in this interval, then ft should lie between fx minus epsilon to fx plus epsilon, okay. Now instead of this, instead of letting t lie between this whole interval x minus delta to x plus delta, suppose I say that t lies only in this interval, okay. What I say that t lies in the interval x minus delta to x, okay, and for that t suppose this happens, mod ft minus fx is less than epsilon, okay. That is instead of this, okay, what I say that suppose it so happens that for every epsilon bigger than 0 there exists delta bigger than 0 such that for 0 less than or I shall say that for x less than x minus delta less than t less than x, okay, that is for all t such that x minus delta less than t less than x, okay. This implies that mod ft minus fx is less than epsilon, okay. Oh sorry, I am not fx, okay, we are talking about limit being L, okay, mod ft minus L less than epsilon, okay. But we do not know anything about what happens if t is in this half, okay. If this happens, we say that this L is a limit of ft as t goes to x from left, okay, okay, and that is this notation. We say that L is equal to f of x minus, okay, left hand limit, okay, right. That is instead of letting t lie between x minus delta to x plus delta, we say that this is true, mod ft minus L is less than epsilon is true for those t which lie between x minus delta and x, okay. It may or may not be true for this part, okay, it may or may not be true for this part, okay. Okay. In a similar way we can define what is meant by f of x plus, okay, instead of taking x minus delta less than t less than x, okay, we take x less than t less than x plus delta, okay. So whatever is that number will be called the right hand limit, that is limit of ft as t goes to x from right. Instead of this minus sign here we will put the plus sign and this number L will be denoted by f of x plus, okay, right. Another way of saying that is in terms of sequences, okay. What we have seen is that, see suppose forget about this minus, suppose limit of fx as t tends to x is equal to L, okay. We have seen that is equivalent to saying that if you take any sequence Tn converging to x, then f of Tn should converge to L, f of Tn should converge to L, okay. Only modification in this left hand limit will be that instead of letting the sequence Tn to be lying anywhere, okay, I will take only those sequences Tn such that every Tn is less than x, okay, only those sequences Tn. So suppose the whole thing is happening in the interval a to b and suppose x, in fact that is how we started, right, we took f from ab to r and x is some point in ab, okay. So suppose this is the interval ab and x is some point here, okay, then I take only those sequences which lie in a to x, okay, which lie in a to x. So suppose you take only those sequences which lie in a to x and suppose for every sequence Tn converging to x, f of Tn converges to L, then that L will be called left hand limit, okay. So we can say that okay, so we say that f of x minus, or which is same as limit of our notation, limit of ft as t tends to x from left, okay, t tends to x from left, okay, that is this is equal to L, this is if and only if, that is this is same as saying that for every sequence Tn, in the interval a to x, for every sequence t in interval a to x converging to x, f of Tn converges to L, okay, f of Tn converges to L. And similarly for the right hand limit we can say that if you take any sequence Tn lying in this part x to b, and if it converges to x, then f of Tn converges to L. If that happens, then we will say that that number L is the right hand limit. Okay. Now it is clear, it is obvious to see that if the limit, if this limit, okay, let me remove this, okay, if this limit exists, okay, and that limit is same as L, that limit is equal to L, then the right hand limit as well as left hand limit both exist and both are equal to L, okay, right. But it can happen that the left hand limit exists, right hand limit also exists, but they are different, okay, left hand limit exists and right hand limit exists and they are different, okay. So let me just write this, okay, if limit of ft as t tends to x exists and that is equal to L, then f of x minus, that means f of x minus exists, okay, or let me write it this way, then limit ft as t tends to x minus that exists and that is equal to L, and that is also same as limit of ft as t tends to x from right, okay. Okay. So if the limit exists, then the left hand limit as well as right hand limit also exists and they have the common value, and that common value is same as the value of the limit, okay. Okay. Conversely, if both the limits exist, okay, if both the left hand limit also exists and the right hand limit also exists and if they have the same value, okay, then the limit exists and the value of the limit will be the same as that common value, okay, right. So I can say that this is so if and only if, okay, okay. But what can happen is that the left hand limit exists and the right hand limit exists, okay, and the values are different, okay, then obviously it means that the limit does not exist, okay, then obviously it means that the limit does not exist, okay. So let us say that the limit ft, let us say as t goes to x, suppose this does not exist, okay, that means x is a point of discontinuity of f, okay, this if the limit does not exist, this means x is a point of discontinuity of f. Now we can say that it can happen in how many ways, there are two possibilities, okay, either the left hand limit does not exist or the right hand limit does not exist, or of course both do not exist, or what is the other possibility, that the left hand limit exists, right hand limit exists and their value is different, okay. So if this does not exist, then let us say there are two possibilities, okay, there are two possibilities. What is the first possibility? One is that limit of ft as t tends to x minus or limit of ft as t tends to x from right does not exist. Or both, okay, but that is included, okay, when we say this or that it means both is also included, Or what is the second possibility, that limit of ft t tends to x minus and limit of ft as t tends to x from right both exists, okay, and they are different, okay. And their value is different, okay. And limit of ft as t tends to x minus is different from limit of ft as t tends to x plus, okay. When this happens, okay, that is the left hand limit exists, right hand limit exists and their value is different, that kind of discontinuity is called a jump discontinuity, okay. Jump discontinuity or simple discontinuity, or it is also known as discontinuity of the first type, okay. Okay, so this is called jump, there are different names, okay, jump discontinuity, okay, also known as simple discontinuity, or also known as discontinuity of type 1. Okay. Let us second one, what is meant by jump discontinuity or simple discontinuity or discontinuity of type 1? It means left hand limit as well as right hand limit exists, but the values are different, okay. That is jump discontinuity, okay. If one of these limits do not exist, okay, that is called discontinuity of type 2, okay. That is this part, that is this or this limit does not exist, that is called discontinuity of type 2. Okay. Okay, we shall see the examples of this both types of discontinuity. Of course, we already seen the examples, we shall just recall those examples and demonstrate that which are the kinds of discontinuities that we have come across of the real valued functions defined on an open interval, okay. This we shall do in the next class.